Well, hello, ladies, Maggie and Andy. It's so good to see you guys. Happy 4th of July. Really appreciate you guys coming back on this podcast to talk about this paper that was recently revealed to me and kind of explains a lot of what we all are trying to do and accomplish in our lives, trying to rehabilitate dirt back into soil. So without further ado, I'm sure because you've been on here before, we've already heard your stories on how you got here. So let's head right into it. So I think, to start the conversation is maybe to start with some of the terminology. It's been public now for a while that we can use the term POM, particulate organic matter, and MOAM, mineral associated organic matter. But what this paper really does is unlock the missing piece in my mind, which is DOM, dissolved organic matter. So I'll let you guys chime in on your understanding. We'll start with you, Maggie. What do you think about this paper and the discovery or the documentation?
I think this paper is a really interesting overview of sort of what we understand to date about soil organic matter dynamics and how soil organic matter comes to be, because that's still something that this paper is a great overview of what we understand now, but this is not something that we fully understand yet by any means. There are many points in this paper where the authors say, this needs more work, we need to study this, we need to work harder to understand this. But overall, I think the most important part for me is understanding, one, those the three main things that you mentioned: the particulate organic matter, the dissolved organic matter, and then the mineral associated organic matter. But then understanding how those come to be in different systems, because there is no one soil. There is no one way that soil exists on our planet. There is no one climate or topography or any of those things, one set of biota that causes soil organic matter to form in a specific way. If there were, we'd have this figured out by now, but it's a very complex system. And I think the flexibility that this sort of model and this paper synthesizes really elegantly, I think, is really beneficial to our understanding of the whole system.
Well said. Well said. Again, it's always about, we need to do more work.
Always.
Andy, what is your opinion on the paper overall?
Yeah, as someone who's working in a capacity of what I'd call like applied science, like trying to take something that has all this gnarly jargon and technical aspects and like translate it to a lay person or somebody who's farming land or restoring a site, that's where my head goes when I read something like this, is like, okay, I can understand this from a scientific perspective, like what we now understand about organic matter formation and persistence in the soil, but how does that translate to what's actually happening through land management? And this particular paper did incorporate more discussion around that than papers I've seen in the past that are discussing more of like the defining what POM and MOAM are. This one kind of took it a step further and said, this is how this relates to common land management, and even comparing like natural state context, more like wild context compared to like heavily managed context. So for me, that's what I'm excited about, is just being able to take this information. And now when I think about someone who's consistently, say, top dressing their fields with compost, but they're not really seeing an improvement in soil health, I have a new set of tools to kind of explain what's actually happening there. Like their organic matter might technically be going up in some cases, but they're not seeing an improvement in their soil health. And this is like the behind the scenes version of what's going on there on the land. So yeah, I appreciate you sending this my way. I hadn't seen this one.
I think, guys, we need to actually bring up and talk about what you guys are talking about, because you've mentioned this document, but nobody has a clue other than the three or the four of us what the document is. So I'm going to bring it up, and Leighton, maybe you can give a quick explanation before we go further on it.
All right, so you're going to bring up that first diagram. There we go. Perfect. So what Andie was just referring to is when you put down a compost on the surface of the earth, you're going to lose 50% of it out of the gate just to oxidization. The biology is going to, of course, get oxidized. And you're not really going to get the kind of return that you typically would if you tilled it in. And unfortunately, in a lot of cases, that's just not an option. Like, you can't till it into a sports field or a prairie or a common ground. You destroy the property. So that's the problem with top dressing. And I mean, when I was first getting out into the world, probably in 15, top dressing was the whole thing. Everybody was running around with these compost screeners and these little ride behind carts where you put the compost in the top of it and you drive the cart and it spreads out an 1/8-inch layer of compost. Now, the other part of that practice was that they didn't realize was you really needed to make sure the grass was long and that you watered right after it. And the one gentleman that I saw doing that practice where he left the grass really long and then immediately after top dressing watered it, did have good results, whereas a lot of other people who top dressed did not. And it's exactly what Andie was saying, is that you lose a lot to oxidization. And so I think that's the important thing to understand, is that, yeah, we have these two functioning groups of POM and MOM, and now what we're talking about is DOM, dissolved organic. And I think that's where, when I first read this paper, it was like, that's the reason why when I do an application, it works so well, is because it's penetrating down. It's taking the existing soil organic matter in the form of sloughed off roots or leftover plant debris and helping to push it down into the soil matrix where it can be a lot more beneficial. So I think that's kind of where we started. Whoa, Cheeto, don't knock over the camera, buddy. So that's where we started. So maybe it's time that we, skip down to the next, or actually, ladies, when do you want to explain that diagram for the audience? Because it's difficult for me to see. My eyes are just not as good as I used to be. So I'll pass over to one of you guys.
I'm happy to take a stab at it. And to be fair, I think a lot of this is going to be more in Maggie's expertise, as I understand it, since mine is more limited to biology, and a lot of this is kind of the biogeochemical interface. So I'm going to try to put it in as simple terms as possible. And if Maggie wants to kind of expand upon it, I think that could be a good way to go about it. But in this diagram, we're looking at the different kinds of organic matter as we know them today, one being particulate organic matter and the other being mineral associated organic matter. And then you see kind of the arrows pointing to how each of those is formed. POM, so particulate organic matter, is it's primarily formed through plant residues that are broken down just during typical decomposition, and some of that decomposition will create soluble, like the dissolved organic matter, which isn't depicted here, I don't think. While basically the biology that's working on the POM, on decomposing it, it can result in compounds that become mineral associated. So those compounds basically will adsorb, like adhere to a mineral and become more stable in that state. So it's actually going to be stored longer term in the soil, that source of carbon, because of that mineral association. However, and we can kind of get into the weeds of this, is like, my understanding is that mineral associated organic matter is water soluble. So in theory, it's easier for microbes and plants to take up. It's just that it's not as easily accessible in the soil because it's associated with minerals, whereas particulate organic matter is more prolific and easier to be found by microbes and in association with plants and exudates.
So Maggie,
I don't want you to I don't want you to sell yourself short, Andie, because that was really good.
I hope I got most of that right, but you checked my work.
No, so in this diagram, it's interesting the way that the two different types, there's organic matter sort of on the top of the soil, if we start there. And this, I'll just go over my understanding of this. And Andie covered most of it beautifully. But there's kind of like this dead branch on the left, and that's like basically shredded. So you might have heard of shredders, like organisms that just take big things and make them into little things and pull them down into the soil. And that's where we get palm. In this paper, they also call it structural. So things that were once the structures of plant tissues that have now made their way into the soil in the form of smaller particles, sometimes teeny, teeny, tiny, but they're still particles of organic matter. On the other side, and I think the DOM is represented here, but just it's really hard to miss. It's those little water drops coming off the roots. So in the form of root exudates, and also coming off the leaf litter on the surface of the soil. So that would be things that are dissolved via rainwater or other things processing that leaf litter that's then making its way into the soil. And on that right side, things get a little more complicated. You have your in vivo processes and your ex vivo processes. Your in vivo processes are basically microbes finding this material and putting it into their tissues. So using it to create themselves or reproduce or poop or do whatever microbes love to do and then die. And more often than not, they do this on the surface of aggregates. So microaggregates, macroaggregates, or the surfaces of particles, sand, silt, and clay. And the resulting chemical transformation of that organic material results in a strong organo-mineral bond that is really hard for future microbes to access. And this paper goes more in depth about the different ways that microbes might be stopped from processing organic matter. But I'm not gonna, because like you said, Andie, it's really easy to get in the weeds. This is like all weeds, honestly.
Yeah.
But I'll stop there for now. And then the ex vivo processes are basically when this dissolved organic matter finds its way to a mineral surface and adheres chemically for whatever reason. So it ends up stuck to it. So that would be something that just happens naturally. Like when you drop salt in a glass of water, it dissolves. You don't really have to do anything to it. It just happens. The chemistry makes it happen. It's the same thing here. And as Andie said, that mineral associated organic matter is more persistent in the soil because it is held tightly to the soil itself, whereas the particulate organic matter is just little bitty bits of organic matter that still might undergo processing or be encapsulated in mineral soil particles and then be trapped in a different way and therefore more persistent. But along the whole way, you have decomposition processing happening, and that's what the CO2 arrows out the sides are. That's showing that microbes are processing this, and like Leighton said, as soon as you apply things to the soil, organic material to the soil, you lose it. And one of the shocking figures that I remember reading in this paper was that you lose anywhere from like 66 to 97% of the organic matter just to respiration. That's how it goes. And then there's the talk of like soil organic matter efficiency, all of this stuff. But I'm sure we'll get into that later. But basically, underneath the figure, you can see the descriptions of the two types of organic matter, POM and MAOM. The particulate organic matter is less persistent. It doesn't last as long. It's lighter. It's got more complex molecules in it, and it's got a higher carbon to nitrogen ratio. Whereas the mineral associated organic matter is more persistent. It's heavier because it's associated with those mineral particles. It's not as complex, so the molecules are simpler, probably because they've been processed by microbial, things. And it's got a higher carbon to nitrogen ratio. So it's a little more stable down there. But I think that might be enough for now as we and somebody else can talk.
I love
yeah.
it. You guys are wizards, man. So the couple things I'd love to just buff on those is that where the mineral associated organic matter does have a longer persistence, I think it's due to what we call electrons or bonding. So water, H2O, right? Simplest thing on the planet, like we should be able to make it, right? It's 2 hydrogens and 1 oxygen. How hard is that? We can't make it, right? So it goes to show you that these bonds, in this case, it would be a covalent bond, become very stable once they've completed their bonding. And this is a little bit out of the gate, or a little bit farther out on understanding like mass. Like just recently, we've all heard about the giant collider over in Switzerland and the Higgs-boson particle. And people, I'm sure, all over the world, like, why is this so important? Why is this so important? Well, we're trying to understand mass, right? And bonds. And the interesting thing is that the subatomic particles that make up a proton are actually, these 3 different smaller particles, moons, damn it, not bosons, but bottom line is the molecular weight of those 3 little particles do not equal the weight of the proton. And what they've figured out through the use of Higgins is that it's that bond that makes up the rest of the mass. So why is that important, and why are we talking about that here on now, about biology and organic matter? Well, that's the whole point, is that bond is creating another structure that is supporting aggregation, right? We all talk about how important aggregation is, and that is when these particles come together, that they bond together in a water stable form. So water can't just wash the particulate or the aggregate away. It's very stable. As a matter of fact, there's pictures of people taking these aggregates and throwing them in a cup of water, and they float. And in another case, you take some soil that's less so aggregated, like a typical agricultural soil, and you throw it in a cup of water next to it, and it all just sinks and falls out of solution, or falls into solution and pools up at the bottom. So that's why these things are so important. Now, one of the things that really fascinated me about this paper is that they say that MOM, mineral associated organic matter, is actually more biologically active. Did you guys pick up on that, or was it just me?
I remember balking at it actually a little bit, because the first paper I read about this, and I don't know that I'm saying this last name correctly, Lavallee, the
Yep.
2020 paper that kind of introduced this terminology. My understanding was that it wasn't as microbial active, like you wouldn't find as much microbial activity in mineral associated matter compared to particulate matter. So that's my only comment on that. I was surprised to see that.
Maggie, you got anything to say?
Yeah, from what I understood, I guess my impression of it was that mineral associated organic matter is more present in soils where there is more microbial activity. And that's because microbes have an opportunity to process the organic matter that comes into the soil. So it has the chance to be turned into those lower complexity, higher carbon nitrogen ratio molecules that more readily form those organo-mineral complexes that make up the mineral associated organic matter. So you would have a higher, more microbially active soil that would be more dominated by mineral associated organic matter, whereas the particulate organic matter is present in soils that aren't as microbially active, and that's why it persists somewhat longer in those soils. That's why it's there. Because the only other way for mineral associated organic matter to form would be, like we said, through this dissolved organic matter, where it comes from somewhere else already in a form that can adhere to a mineral complex of some kind, and then be persistent that way.
Nice. Nice.
Yeah.
And Andie, I was all over it. Like, I was like, that's not right. Right.
Yeah.
Everything, all my work shows me, like, when I take a compost and compost it down till it's
You lose it. Yeah.
you know what I mean? And then there's hardly any microbes in it. I mean, the work that you did with me on figuring out the bell curve of, you know, the microbial expansion indicates the older it gets, the less microbial it can be.
Yeah, and this, just to relate it to what you're talking about, Leighton, with compost, it's using Maggie's explanation. This is why GOM, ground up organic matter, the shorthand that we tend to use for industrial compost that just grinds up a bunch of, you know, feedstocks coming in, doesn't keep ratios right, it heats up, it kills off almost everything except bacteria, then you don't have those shredders and decomposers and the full suite of biology to convert that source of organic matter into POM and then mineral associated organic matter. And so it can be confusing when you look at a fully processed healthy compost that did have all of those soil biology characteristics, that then you lose the the abundance of beneficial biology towards the end of that process, because it's becoming more mineral associated. And so the microbes have essentially done their job, and there's no new sources of incoming organic matter to keep that process going. So it's cool to hear your explanation and perspective, Maggie, because that really helps us think through composting and why, and like, again, trying to explain to someone who's making compost that doesn't have a lot of life in it, from a biodiversity perspective, it has plenty of bacteria, it has lots of bacteria. So that is a life form, but it's just not the full suite that can really lead to this process of organic matter. And that's something else in the paper that kind of stopped me, that I really had to think about, was there was talk of wanting to basically like limit microbial activity because of like how much CO2 is lost. Like there was talk of being interested in slowing down microbial decomposition. And I thought, if you don't know any better, you might think that that's like, you know, a feather to put in your chemistry hat instead, you know, soil chemistry approach rather than soil biology. But the thing is, if you think of like bacterial blooms, I think that's what is being suggested there, is that bacterial blooms will blow off a lot of CO2. But when you're leveraging the full suite of the microbiome, that's when carbon's moving in the right direction.
Well, and I also think too that like talking about slowing down, they also talked about three, what did they call it? It was like three inhibitions essentially to SOM breakdown or the processing of SOM. And the first was a microbial physiological limitation, which is basically where it's too damn cold and the microbes can't process stuff, or it's too wet or whatever. The second one was a microbial metabolic limitation. And maybe I'm getting these mixed up. Hold on. Let me find my notes on this, because I remember thinking.
Yeah, you find your notes, Maggie, because there's another point.
Go ahead. I have my notes, but if you want to say something, go ahead.
Well, and again, like, people are being misled about CO2. I'm sorry, CO2 feeds plant life. Plant life feeds soil structure, soil building, animal health, the whole ecosystem. And so to slow down, in my mind, is the worst thing that you can possibly do. Now, again, we're talking about soil that has plants on it, right? You're not going to have the formation that we're talking about, soil organic matter formation, in a desert, right? That's not going to happen. So please, let's make sure we're staying in context, the listeners, that we are talking about a situation where you have soil and plants, and not bulk soil. Bulk soil would be the soil in between the plants, where there is no roots or microbial interactions with roots and obviously the rhizosphere. So I think that's important. And the other one, you nailed it, Andie, is long-term carbon storage. And that's what's happening. So what, you're losing a little bit of, carbon in the CO2 bond, but you're building solid aggregates of carbon, which are the critical tool that microbes need when they're assimilating nitrogen into and other elements too into plant available forms. Okay, sorry, Maggie.
No, I have thoughts about all that too. But I do want to get to this important point because this is a really fundamental thing to understand. The microbial physiological inhibition, which is they talk about in this paper, is it's too cold, it's too wet. I can't move, I can't breathe. Those are the two things that make it physiologically impossible for microbes to process organic matter. That's when we get soils that are extremely high in particulate organic matter, like our peat soils, our histosols, right? So when we have those soils where plant life grows and dies and doesn't do anything else, it just doesn't decompose, nothing really happens because it's too cold and it's too wet, and those microbes can't move and they can't breathe. The second one is the microbial metabolic limitation. So that's the next step down, where my microbial processing is still happening, but it's limited in some way. There's not enough nutrients. It's too dry, so things can't move around. They can't access things from other places. But it's their metabolism that's being limited somehow. Also, energy, it says here, is a limitation. This is the same thing. You get soils that are higher in particulate organic matter. There's higher carbon to nitrogen ratios, and the soil organic matter is vulnerable, just like with the physiological inhibition, it's vulnerable to changes, right? As soon as it becomes warmer or wetter or more aerobic, that particulate organic matter, gone. Mm-hmm. Then there is the microbial access constraint. And this is where we get into talk of aggregates. So this is the form of microbial inhibition that makes soil organic matter physically inaccessible to microbes. There are a few different methods of, like in theories of aggregate formation, macroaggregate, microaggregate. We won't get into that unless we want to. But long story short, there are aggregates and soil organic matter is generally trapped within them. This happens by and large because microbes eat the organic matter, poop, and then make these exudates, and it causes mineral matter to adhere to them and their necromass, their dead bodies. They form like this little gross shell of organic matter and exudates that are all glued together inside a little ball of minerals, usually clay-sized minerals. And then those eventually result in larger and larger aggregates. That's one theory of formation. There's others, but again, we won't get too in the weeds. But at that point, at which it forms that little glued together ball, the stuff that's in there is not accessible to the microbes outside of it. So we can fractionate those pieces apart and find it in there, but the microbes can't. And that is the most persistent form of organic matter. So we want that to happen in our soils where it's not too cold, it's not too wet, the moisture's just right. I mean, we're in a real Goldilocks zone here for most of our stuff. And that's the importance of, like, keeping the carbon in the atmosphere low. We don't want hothouse earth because then we can't grow the things we're used to growing. We can't live the society that we're used to living in, yada, yada, yada. But that's a really important thing to keep in mind, is that these aggregates are really important. And actually, back to something you said earlier, Leighton, about tillage, I don't want people to get confused about tillage because, like you said, when you incorporate the organic matter, it's more readily processed and then turned into soil organic matter by these microbial processes. It happens faster. Just top dressing, it doesn't happen very fast. However, when you till repeatedly, you break down those aggregates, you expose all of that organic matter, you reduce the soil structure, and then you have a completely different problem, which is concrete soil where you can't actually introduce anything more at all. It stops the functioning. So there is a balance to strike. And I mean, that's why this dissolved organic matter thing is important. That's why growing plants in place. So no-till practices often involve cover cropping. And it's because that cover cropping grows roots. And the roots produce organic matter that causes that allows the microbial community to flourish. It produces the particulate, the dissolved, the mineral associated organic matter, keeps the soil aggregated in place, aerated, all of those things that we want without that tillage. So we can get plants to do the incorporating for us. But yeah, I mean, like you said, just top dressing is not enough, but there's other ways to get it down in there.
Yeah, if I could piggyback just briefly on that, you know, even if you top dress, let's say in a small scale context where this is practical, if you're top dressing, say, a community garden or a small farm, just mulch on top of it, you know, like protect it, put more particulate, or like that's just another source of what could become fodder for particulate organic matter according to these processes. So you would limit the amount of oxidation of that top dressed compost if you protect it with some kind of leaf litter mulch layer on top, and then you're effectively honoring the principles of this process. So, you know, after reading through this paper, it's like it really comes back to the soil health principles. It always does, you know, and the biggest one that we've been talking about so far is context. So we do want to, I do think this is a misnomer that, like, if I had any beef with this paper, it's the use of the phrase of inhibiting microbes, like microbial inhibition being like a desirable thing. The thing is, you have to realize what that means in any given context. So in the context of peatlands, we don't want to disturb that site because we want to maintain the carbon in that particulate matter state so that it's not digested and released as CO2 into the atmosphere. Same thing with like permafrost, you know, as those kinds of sites, all of that carbon that's being stored underground and then thawing and then allowed to decompose and you know, respire, that's becoming hugely problematic. Now, in the context of like agriculture, microbial inhibition is a little more nuanced, at least in the way that I see it. When you're tilling, you're destroying a lot of the habitat and structure that would be there. And as Maggie pointed out, like exposing that mineral associated organic matter and releasing that when it could have been a long-term storage of carbon. And that's essentially inhibiting microbes, like the microbes that we want there, but it's increasing the amount of activity among the bacteria, which are the least carbon efficient, right? So if I'm a bacteria, I'm taking in roughly 20% of the carbon and putting it into my body that I'm eating, and I'm releasing 80% as CO2. But if I'm fungi, I'm doing the opposite. I'm taking in 80% and releasing 20%. So that's why like fungal biomass is so important to carbon sequestration and long-term storage, because of all that high surface area potential they have to store carbon in a much more meaningful, efficient manner than bacteria. But we can't maintain good fungal biomass if we're practicing things like tilling or exposed ground and all of the things that kind of fly in the face of soil health principles.
Love it, you guys. Love it. This is exactly the conversation I wanted to have. And again, you know, tillage is a tool, but it's not for everybody, right? In certain circumstances, if you're trying to jumpstart something, yeah, it's important that you got to till in all of the existing plant material that you don't want to be there. And you've got to also, you know, provide more of this like GOM, because it's still going to hold water. It's still going to provide food sources. And that's going to get you jump started. And then from there on out, then yeah, roll or crimp, you know, cover crop, do these other methodologies that don't disturb the soil. And the other piece,
I'm sorry.
I was going to say, and the other piece on the fungi too is that in these fungally dominant soils, you're getting water transportation, you're getting nutrient transportation, you're getting aggregation on steroids. I mean, in many ways, those fungi are the architects of the soil. They're the ones that are help support building of these aggregates that are so important. And just to bang on one other thing, Maggie, in my pea brain, I look at the aggregation formation as a way to create a castle. You've got all of the things you need inside there. You have that mineral associated organic matter that you can use as your population expands and goes through generational, generational expressions. In other words, your kids have kids, your kids have kids, your kids have kids, and that they have everything that they need in that aggregate. And then, like, I love what you said about how they expand, because now on the outside of that aggregate, you're having a different community of biology that are performing different tasks. And of course, they're excreting their biofilm and creating more sticky surface for more clay and more silt and more sand to stick to the aggregate to continue that expansion out. So anyway, that was my little caveat on understanding the aggregate formation. And I believe in that theory more than I believe in any of the other, I'm not going to say cockamamie, but other theories on that. Now, I'm sorry, Andie, go ahead and add on whatever you.
Oh yeah, no, it's just on something that you mentioned about tilling and stuff. It's like, how cool is it that we now have technology where we can kind of differentiate what type of organic matter we have in the soils, right? So if you can confirm that, let's say you are on a site that you want to farm, and you can measure the mineral associated organic matter in that soil compared to the particulate, then that is going to inform how you go about whether or not to till or not, whether or not to incorporate compost or other plant biomass in a certain way. Like maybe you decide, actually, it's better that we not disturb it at all. We're going to chop and drop. We're going to go about it differently. And that's what this technology and these kinds of insights really unlock for us, is coming back to context, using them within our context and making informed decisions about how we go about managing that land.
Yeah, this is a dangerous topic because of the context. Everybody's application is different. It's like you have to really drill down to understand what tools you have and which tools you should use and which ones you shouldn't use. And that's kind of where I went back and said, okay, basically what we're talking about is a soil system that has plants, not a system that is void of plants or has been abused to the point where a very few plant species can live there. I hate the term weeds. I love the term indicator plants. So where you only have a few indicator plants, and the field could have been followed for 3 years and it's not functioning. It's in deadlock. It's not going to be productive unless you do something pretty drastic. And at the end of the day, if you could do a DOM installation, then you don't have to till, right? And that's why I was so excited when I saw this paper, and I figured, hey, I got the two best people in the world to talk about this.
Flattered.
Yeah, I think the dissolved organic matter idea is very interesting, and I'm actually just now reviewing my notes about some of the things they said about the dissolved organic matter. I think it's important to be careful about dissolved organic matter, because it's not like we can just sort of liquefy, all of our organic residues and then apply them that way, and then that'll work, because it won't. It won't promote the aggregation that we want. It will result in leaching to groundwater of important nutrients. But the dissolved organic matter idea is it informs how we think about what happens in the rhizosphere, how that rhizosphere activity results in mineral associated organic matter, how leaf litter can turn directly into mineral associated organic matter. And dissolved organic matter has been a concept in like stream biology and stream ecology for a long time. They have known about this stuff. It's like a thing. And we're finally catching on in soil science. And it's really important to understand. And one of the interesting things they said in this paper about dissolved organic matter, and I'll just read the quote because I think it's interesting. They said mechanistically, the biotic role in MAOM, so mineral-associated organic matter formation, has also been suggested to depend on the point of entry of the dissolved organic matter, with dissolved organic matter leaching from above ground residues having a lower probability of being assimilated by microbes than the dissolved organic matter entering directly below ground through the rhizosphere. So this reinforces what we already said, right? When we just put leaf litter on the surface, some of that might turn into organic matter, but it could also just like leach through and result in groundwater contamination. But when plants produce exudates, which are present in microbially enriched areas, it results in more conversion to soil organic matter. And what frustrates me about a lot of this like soil carbon talk, it's important to understand all of this functionality. But I think some people pretend like we won't know what to do with our soils until we understand all of this, when we've known exactly what to do for a very long time. We have to not disturb the soil as much as to the extent that we can. We have to feed it with organic, complex, enriched materials as much as we can. We have to avoid allowing it to wash away, especially those finer particles like silt and clay, because they provide a lot of those adsorption surfaces for that mineral-associated organic matter. Sand is effectively inert. We know what to do. And now this informs like why it works, but the practices have been around for ages.
Totally. It doesn't take a scientist to say we're improving the soil health here, you know?
Not at all. Yeah.
And, that's such a good point about understanding, again, how to use this, Dom. And so the interesting thing is, I think there's another picture that we should pull up. I think it's probably like the third or fourth diagram, and it shows the relativity of POM, DOM, SOM, MOM, POM, and DOM, and it shows on a graph, Ken, that goes down to a point, and it basically explains that this dissolved organic matter is like 1 to 2% of the overall soil organic matter pool. Yeah, that kind of helps. It was actually like that. No, not that one. There it is. So, yep, that's the one. All right. So as you can see, when you look at these solubles, see that's just a tiny fraction of the overall pool for some, right, for the soil organic matter. And basically that's primarily exudates that are being leaked from the plant. Like you said, Maggie, there's a small percentage of, say, the leaf litter that gets rained on that breaks down or has been shredded to the point where it can break down or solubilize to some degree. But the interesting thing is when you get into like my line of work where I'm making this been a Monday, dissolved organic matter by taking compost biology, worm castings, and then using mechanical systems to liquefy it, break it down further, and then screen it out, and then apply it either through a soil drench or through injection. But the results, the plant reaction you get when you do this is insane, Maggie. It's just crazy what I've seen in, even to this day. I've been doing this for 15, 16, whatever years now. And it still blows me away that I can take this, compost that's biointensive, add some fish brew, add in some worm castings, agitate it, and then apply it, and then get plant reaction. With brassicas and grasses, you get it within 24 hours. With trees, you might take up to a month, but the results are insane. And it always made me wonder, like, what is it that we're doing? So I had James White on, Dr. James White, and we talked a little bit about how DOM affects the rooting system, the roots of the plants. And the interesting thing that he pointed out was that what happens when you have, a soil system that's functional. So it's got to be aerobic. It can't be compacted. So again, there's the little disclaimer there. But you say you have a potting soil or an aerobic soil of some kind, and you plant a plant, and then you apply these dissolved organic matters. What happens is the plant, instead of throwing out a tremendous amount of lateral roots or searching roots that go out to try to find these mineral pockets, basically you end up with a taproot with a ton of root hairs coming off. And he also clarified that those root hairs are actually the rhizophagy cycle, and so they're relatively small, maybe a few centimeters. And what happens is on the root tip is where the interface between the biology and the plant happens. So the plant will allow that bacteria into that root tip, where it strips the outer shell, assimilates it into a plant cell somewhere along that chain of root, and then excretes it back out for it to go all the way around that root again until it comes back to the tip, where it gets brought back in, because now it's pulled in nitrogen and some of the other minerals. So it does have a really interesting effect, because with all that excess energy, now the plant's putting it toward vegetative or fruit growth, and not worrying about sending out all this, soldier roots to go out and find these pockets of mom, because that's really what they want. They want those mineral associated aggregates, because they're the ones that are providing the minerals, whereas the POM is less likely to have the concentration of minerals that we can associate with the more stable MOM aggregates. You guys want to add on something to that little rant?
I want to be careful about this graph, because this is actually what you're saying is like correct and reflected in the paper, but this graph represents the former understanding of soil organic matter formation. So in the past, people thought that molecules like lignin, lignified carbohydrates, the yellow and the brown on this graph, represented more stable organic matter. And you can see that by the way that they don't really get any smaller over time. And then they thought that the soluble, the dissolved organic matter, was rapidly utilized and then dwindled to virtually nothing. And the cellulose and hemicellulose was the same. They were rapidly utilized by microbes and they weren't very persistent. But lignin and lignified carbohydrates were persistent because they were more complex molecules. But what we understand now, and what they're saying in review through this paper, is that the dissolved organic matter sort of primes the soil for microbial functioning, which then allows microbes to take that lignin, the lignified carbohydrates, these more complex molecules, and turn them into mineral-associated organic matter, which is more persistent over time, but they're no longer those big complex molecules. And there was a quote that I thought about, but I'll try to find it. Andie, if you want to say anything about this.
Yeah. Well, first, Ken, if you go to page 10, there's a diagram so this diagram that's been up was the former understanding of how soil organic matter was formed. But this is the graph that represents the quote unquote 2-pathway model of organic matter formation. And so as you can see, it's like a lot more complex looking. But as Maggie was saying, those first like 3 triangle colors are basically priming the soil to be able to break down things that are more complex, like lignin. And all of these have the capability of becoming particulate organic matter and mineral associated organic matter.
And you guys, I apologize. My eyes suck. I can barely see. There was another graph that showed how those different forms of soil organic matter are utilized or introduced into soil. And that one that I asked Ken to show was what I thought was the graph that I was looking for, but it's clearly not, because
there's another one too. We might want to spend some time on this one. So Ken, I wouldn't move off this one just yet, but there's another good diagram on page 12 that might be what you were thinking of, Leighton.
Okay, so yeah, let's beat this one up, because this is important to understand. Is because what happens? What is compost? What is plant matter? Right? It's those components that are the function, or that provide the food for the biology that builds the soil. Right? So, what is the best form? What is a hardwood better than a softwood? Is a leaf litter better than a shell, a husk, right? So I think that is a good point to better understanding how to make a product. If you were looking to utilize dissolved organic matter, how best to make your compost. And Andie, why don't you take that mic on that one?
Well, I think this just provides an explanation for why we harp on having diverse feedstocks, of differing complexities, because you really kind of need one to prime the system to help break down the next, so you also end up feeding a suite of organisms that can do that for you in the soils. So like if you think of compost as being an incubation of beneficial soil biology that you then want to apply to your soils, you want to have a lot of different food sources for them, so that you're raising the microbes that will be able to immediately upon entering the rhizosphere be able to process all of these different forms of organic matter. And so, when I think about practical applications of this, a lot of people might see that their mulch isn't breaking down. Okay, like a wood mulch. If it's not breaking down, that probably means there wasn't this stage of priming the soil, conditioning the soil in a way that it has the resources it needs to process the lignin in something more recalcitrant, like wood chips. So those are like signs that I would be looking for, and then working backwards. Okay, if we're not having our lignin-based feedstocks breaking down in our compost, or if it's not breaking down on the land, how do we work back to some of these simpler cellulose-based organic matters, or even more like soluble forms of organic matter to kind of kickstart that process?
I love it. And you know what? It goes back to what you said earlier. How do you make a good bio-intensive or biocomplete compost function in a top dress? You throw down a bunch of chips on top of it, right? I mean, out here in California, we have what's called chip walks. So they use chipped up trees in the walkways instead of concrete. And it's really cool because it's comfortable to walk on. It's not as hard on your knees and your joints. For me, the old man, to walk on chips versus walking on concrete. And I know the pups love the chips way better than the concrete as well. And if you dig down, you got to go pretty deep in these chips to get down to the bottom, but you have this amazing soil that smells amazing. And that's that interface that you're talking about, where the microbes are of the right kind to break down those more recalcitrant chips that are on top of them. So I'm glad that you made that point, and I could, exasperate on another way to install a really good compost by burying it in chips, or not burying it, but you know what I mean, adding a decent 2-inch layer, 3-inch layer over the top of it. Maggie, did you want to add something to this conversation?
Yeah, I mean, this figure is actually kind of difficult to understand if you're not really sure what you're looking for. Andie did a really nice job of explaining the big point of why they even included it here. But just for aiding in people who are like looking at it, who don't know what they're even like looking at, you can see, so the very first triangle, as Andie said, is, they call it non-structural, right? That stuff that's dissolved, that's just particles. Then the next triangle and the next triangle, those things get broken down after that dissolved organic matter. But those three things, upon initial decomposition, go down the DOM microbial path, right? They get assimilated by microbes and turn into necromass or whatever, and then form complexes with mineral associated, or form complexes with minerals to form mineral associated organic matter. That priming results in an increase in activity that allows those more complex molecules to be broken down, but they aren't broken down in the same way. They don't undergo a chemical transformation in microbial tissues. They get broken down physically. So they turn into those particulates, which then aren't as persistent, which get broken down and turned into that mineral-associated organic matter, theoretically, later. But it takes longer to get to that. The dissolved organic matter is therefore more stable because it becomes mineral-associated faster, and it doesn't undergo as much loss. Whereas the particulate organic matter, the bigger molecules have to get shredded, they undergo respiration, and there's a lot of loss involved before they actually turn into a mineral-associated organic matter form. So this is like a really complex sort of idea, and it flies in the face of that initial like, oh yeah, the dissolved organic matter it gets used and then it's gone. Because that's not true. The dissolved organic matter is used and it stays. And that's the really like fundamental shift in our thinking about soil organic matter. But as far as like the applied science of that part, that has been well covered by you two. So I'm not gonna touch that.
Oh, the perfect panel for this. All right. What was that other chart that you wanted Ken to pull up?
Oh yeah, page 12. That's it. What do you think of that?
Well, again, these are these subtle things that are really hard to see. And Maggie, thank you for pointing them out. But if you look at the DOM, those are little water drops. And if you look at the palm, just above it, those are little sticks or twigs or broken pieces of plant material. So it gives you a better understanding of like the transportation method, right? So palm generally starting on the surface of the soil has to be shredded and dragged down, whereas the DOM naturally migrates downward if, again, you're in a soil system that allows for infiltration. And that, again, please keep these things in context. If you throw DOM down on a crusted soil, forget it. It's just going to run off or evaporate. It's gone. So it has to have a soil system that'll accept it. So here again, in the case of say a dysfunctional soil, a prairie, a sparse piece of property that only has a few indicator plants on it, the way to start the interface is to till if you have to. If you don't, you can, and you have the resources, you can apply a 2 to 3 inch layer of good compost, and then another 2 to 3 inches of good chips, and then apply a compost extract. Now you're going to start to get infiltration. Not immediately, but the compost will soak up that liquid and hold it in place while the process begins. And in situations like this, where I've been forced to deal with soils like that, like out here in California, I mean, I was brought onto a project and said, oh yeah, we just need compost tea. And I was like, no, I'll be happy to waste your money if you want, but anything I spray on the soil is just going to run off down the hill. And so this is exactly how I went about it. Was I basically raked back all the crusty soil. First we watered, obviously, because you can't just rake crust back. So we watered it, broke up the crust, raked it back, exposed the root ball, put down the compost, put the drip irrigation down, put the chips on top, turned on the irrigation, and they had plant reaction within about 2 weeks. So we know it's possible. And then over time, that DOM goes down and associates with those the minerally rich components or aggregates that are forming. And so I think this one really helps you understand visually like how this is happening, and better yet, it brings in how the microbes are also interacting with these components. So maybe Andie, you can dance up a little bit on the microbe.
Dance monkey.
Yeah. It's a handball going.
But I do love to dance, in case you're wondering. Yeah, so the big thing I want to point out here about the microbiology part is that you really can't, if you consider where the microbe is at in the process, it just helps complete the process, right? Like technically you can have dissolved organic matter adhering to a mineral and becoming mineral associated organic matter. You can have particulate organic matter turning into dissolved organic matter slowly, and then become mineral associated organic matter. But without the microbe, you really kind of slow things down. So a practical example of this is like around here in Texas, I see a lot of fields where they're starting to leave the stubble. They're leaving like plant litter, and it never breaks down because they really don't have a lot of biology in that soil. And so what do they have to do? They have to burn it. And so you're combusting all of your carbon and nitrogen that was in that organic matter. So if you're seeing signs of things not breaking down, it is likely a biology issue, and that's what's going to unlock this cycle, this process of turning your leaf litter, if you're like top dressing with any kind of manure, compost, that the microbe is what allows everything to kind of move through the system regularly with like some kind of consistency. Otherwise, you're just kind of on a geological time clock being like, where's the nutrients that I need to grow these plants? And that's not how agriculture works, is it?
No.
Right. And that's like why we've relied on synthetic inputs for so long, because the microbes are necessary, like you said, to complete this cycle in any sort of reasonable timeline. Like without it, it just doesn't happen. But we can sort of bypass this system if we use chemically generated nitrogen, phosphorus, potassium, carbon, all of those things. But then what we're missing is the essential functionality of that organic matter that isn't turned into nutrients. And that's what this paper is all about. It's all about that soil organic matter that doesn't become used by plants, because that's where the carbon is stored. That's what promotes soil structure. That is what allows our soils to function in a healthy way. It's not actually the stuff that gets used. It's the stuff that just sticks around. And that's why we keep having these conversations.
And that's pore space for water to be held, for air to be held, so that we can be more resilient during times of drought or times of flood or times, and get off of the tilling, because we'll have the soil structure where we need it.
Yes.
I love the fact you brought up stubble. Years ago, when I was still at Rodale, I was working with a different farmer who grew corn. And, that was always a big issue of, well, how do I deal with the stubble? And they hadn't come up with the idea of burning it, thank God. But basically I showed him, I said, look, if you run this combination of manure slurry and a compost extract and spray it on the surfaces, you're going to get a better degradation, especially in the roots. So he tried it, and sure as shit, we went to where he had a test plot and where, test and control. And you go to the control and you grab that stubble and you try to yank it out of the ground, and it's a bitch. You can't do it. But you went over to the one that was treated and it pulled out, and there was a very little root ball around it. And the same thing has happened, repeatedly when I've worked with the cannabis community on their root balls, because they know the root ball is huge because it's in a pot. They can see the roots coming out of the side of it, but because it's living soil, they harvest that plant and they go back a week or two later and it just pull it right out and there's just a little ball left. So we know that these things are highly functional and obviously missing if you have that stubble. So, very valuable. And did you guys catch that one? I forget what that fourth form of organic matter, like pyrolyzed.
Yeah,
Pyrolyzed.
Yeah.
Or pyrogenic is often the word.
Yeah, that was wild. But anyway, we'll stay on focus here.
That's biochar.
yeah, essentially biochar. Yeah.
And we had a guy on talking about the benefits of biochar, but again, it's so important the way it's made. And I think that in traditional native or indigenous people's methodology of burning off, it was not what we call biochar nowadays because it never got that hot. But what it did do was form something in a soft carbon form, even softer than charcoal or activated carbon. It's something that was relatively easy for the microbes to chew up and provided that extra nutrient back to the soil for the health of the overall forest. But I wasn't intending on going there. I brought it up.
That's a whole other can of worms.
It's like can of worms for sure. Yeah.
Mm-hmm.
All right. There's another diagram further down which actually begins to show aggregates. I don't know if any of you guys pulled that.
Was
up.
it on page 16?
I can't see.
Oh yeah.
Yeah, that's the one. All right, ladies. Who wants to start on that one?
Andie, any thoughts, or should I just go for it?
Go for it. Yeah, go for it.
All right. I thought this was a really interesting diagram. But as somebody who studies soil science, it's kind of like, yeah, this is it. But for the people who aren't familiar with aggregates and understanding aggregates and all of this stuff, on the left is a low organic carbon soil, so a soil that does not have a ton of organic carbon in it. And on the right is a high organic carbon soil, so a soil with a lot of organic carbon in it. And you can see immediately there's a difference in their color, essentially their darkness. The one on the left is not as dark. The one on the right is darker, and that's to represent that higher organic carbon concentration in these aggregates. So there's two types of aggregates represented here. There is the macro aggregate, which is the cloud shape towards the top. And then there is the micro aggregate, which is the larger ball, right? The larger circle. They're the brown colored things. There is also individual particles of silt and clay represented here. You can see in the lower organic carbon side of things that macro aggregate is a lot smaller. On the higher organic carbon side of things, the macro aggregate is larger. There are fewer micro aggregates in the organic carbon soil and more micro aggregates in the lower organic carbon soil. And then in this little circle in the middle, it says hypothesized, but we're not certain. But basically this idea that microbial residue sticks together the particles, the individual particles of silt and clay, and the particulate organic matter adheres to the surfaces of the microaggregates. So there's a lot of different things, a lot of different directions we can go in here. The part that I have here highlighted is these relationships suggest lower turnover of macro aggregates stimulates the accumulation of soil organic carbon and its stabilization via occlusion in macro and micro aggregates. And what they're saying here is basically that when those macro aggregates don't get broken up and the micro aggregates that make up those macro aggregates aren't exposed, there's less soil carbon turnover, meaning there is more soil carbon storage because it is occluded It is kept from decomposition and breakdown inside the macro aggregate. So going back to what Leighton said about understanding, like I'll call it his castle theory about aggregation. There are two theories for aggregate formation. The first postulates that first a little particle of organic matter finds its way into the soil, microbes attack it, eat it, die, poop, whatever. The silt and clay stick to it and it forms a little tiny micro aggregate. And then on those surfaces, the particulate organic matter continues to stick to it, and more micro aggregates form around it, forming eventually a larger macro aggregate. So that's kind of the opposite of the castle idea, because all of the resources are used up in those individual micro aggregates and kept from further use when they form that eventual macro aggregate. The other idea, which is more in line with the castle idea, is that a larger piece of particulate organic matter is attacked and attacked and attacked, and the biota eats, poops, dies, whatever, and the silt and clay sticks to the outside of that larger particle, and then inside it is trapped enough particulate organic matter such that it breaks apart into micro aggregates within that larger macro aggregate. Again, resulting in the end state of like everything inside is like not super active because it runs out of resources eventually, but it all becomes glued together in the inside eventually. But this diagram is basically saying that in higher carbon soils, you form larger macro aggregates with more micro aggregates inside them, storing more organic matter. In low organic carbon soils, you can still get that macro aggregate, which is really important to prohibiting soil organic matter degradation, but it just forms smaller macro aggregates with fewer micro aggregates inside. I said micro aggregate and macro aggregate a lot there, so I hope
you nailed it though. You got them all right.
I hope we are all still here after all that.
Love it. Andie, you want to add to that?
I mean, that's beautiful. I think this provokes a question for me that I'd like to discuss with y'all, which is, you know, when I think of aggregation in soils, I think of creating habitat, right? Habitat for the microbes, habitat for earthworms. It's even easier for roots to move through, right? If there is, in theory, like less activity because you have finite resources inside these pore spaces, and eventually you'll run out of them. I want to hear, like, Maggie, Leighton, do you think of that castle idea or the habitat idea as being like maybe not quite right? Or is it that we're generating habitat kind of around the aggregates, not necessarily inside them?
I guess I'll go first. Originally, you know, when I looked at aggregation, it all started with when I made my product, I would run it through a 47 micron sieve. And if you've ever looked at 47 microns, it's basically like cloth. It's so fine, you can't see anything through it. As a matter of fact, I have a piece over there, but I'm not going to go get it. But I would use vibration to let all of the microbes separate all the liquid from the solids. Dewatering is what it's called, to the best of my ability. And whatever was left in that screen after I vibrated it was muddy, but it wasn't like you pressed it, it just squished out everywhere. It still had a little bit of body to it, so it wasn't like total like slurry. It was more like something that you could make like a snowball out of. So then I go through the process of taking that material and pressing it. So dewatering it even more so that I could get the moisture value down to around 40%, so that when I put it in a bucket or I sent it to someone, it didn't go anaerobic. If the moisture level was too high, obviously there was no oxygen penetration, and this material that I would send people would stink, and I'd lose my protozoa, and I was not happy with that. So That's why I went through this process. So after I went through the second dewatering where I pressed it down, I would then I run it through a screen, again vibrating it, and all of a sudden, all of these little tiny pieces would start to turn into Rice Krispies. And so, like, I called it magnetism. Like it was electronically charged. Electrons were stimulated to the point where they just pulled back together and formed these little micro aggregates. And then, so originally I thought, well, okay, when I'm putting this product into the soil, I'm providing a condominium for the biology. So I'm not just throwing the biology into the soil and hoping for the best, i.e. when you use a GOT brewer versus, an extractor, which Annie, we've talked about. Big difference, right? So, but then when you're charging them and then they pull together the clay, the sand, and the silt, that's more along the first primary theory of how aggregates are formed, is they start very small and then they just expand. And that was my concept until I started fooling around with rhizo sheaths. So what's a rhizo sheath? Everybody that's ever pulled a weed has seen it. It's this like big clump of soil that's held together by the roots, by the fungi, and by the the glues that are formed both from, I'm not supposed to use that word anymore, glomalin, because it isn't. It's a glomalin related soil protein, I think is what the real term is. But that is also part of that thing. But I would take these rhizo sheaths and I'd cut them and I'd start taking different parts of them and putting them in solution and looking them under the microscope. And the diversity was insane. Like, this was a community that had ciliates. This was a community that had huge balls of fungi. This was a community that had tons of protozoa. It wasn't evenly distributed through the whole sheath. In other words, they were like mini cities that were all present. And that's when I started to think, I think it's more a fact of like the attraction, the law of attraction that's creating these. And again, please take this in context. This is in contact with roots. It's not in bulk soil. In bulk soil, that type of aggregation can't form, right? So just to make sure that I'm, speaking correctly and not leaving it too vague that people could misinterpret it. But that's where I went along the more castle theory. It was like, okay, this is happening at a lot faster of a pace. And there's all these different communities that are working together that are creating this aggregation. And is it expanding? Hell yeah. Every time that plant grows or shoots out further roots. And the case example of that is that when you pull that big rhizo sheath up, you'll also have roots a little bit further down that have those little clumps as well that are forming. Anyway, that's my 2 cents on that. And now it's your fault or your problem, Andy.
No. Oh, so did you say my name? I want to hear what Maggie said. I saw some head nodding too while each of us are talking, Maggie. So I know that you probably have some thoughts.
I always have thoughts. The question is whether or not they're like worth getting out there.
Totally.
Now that's it's interesting that you like identified those communities and came up with that theory. My thinking behind that would be, because you're right, that root sheath does form, and it's basically this idea that microbes grow, eat, die, and poop, and then things stick to them that results in that whole bundle sticking together. And the roots produce exudates that also act as like sorts of glues as well, causing that mineral soil material to adhere to it. I would think that soil is a lot more complex and a lot less homogeneous than we give it credit for, especially once microbes get involved. So you'll often hear about anaerobic conditions in soil being when things are too wet, but anaerobic conditions can also happen within an aggregate because it's full of water or it's run out of oxygen, all of these things. But then that process results in a different community of biota taking over inside that aggregate. And what I'm trying to get at here is that all over that rhizosphere, the conditions are different. There might have been a rock somewhere that changed how water flowed around things. There might have been a different starting condition. An earthworm might have gone by introducing different sorts of compounds, or there might have been a fungus there. Like there's all kinds of things that result in varied conditions around the same exact plant that could result in varied communities being present in these sorts of cities, which is a really cool analogy, around the same root sheath. So that's my overall theory about what you saw there.
Andie.
Yeah.
I'm dying to hear your opinion on that.
On the root sheath thing, I mean, yeah, I think it's interesting how, I think what has caught my attention that I'll be thinking on is the fact that you sieved it. It's effectively separating everything, and then they gravitated back towards together, likely in a different combination than how they went in, right? And so that to me is like speaking to, you mentioned like more of a magnetism, like more of the like chemical and physical properties, and then but the biology is nonetheless there. And so I don't have any thoughts. I think you just like kind of dropped a thought bomb on me, and I'll be thinking about it and text you probably Friday and be like, hey, I have some ideas.
All right. So just to make sure you're not confused, when I talked about the Rice Krispie formation, that was after I made product. But the rhizome sheath, when I cut through it and then took different samples from different areas of that sheath,
sure. Yeah,
where I had all those different environments, that was just kind of like, whoa, like what? I never thought that there would be that level of diversity.
yeah.
And then it's kind of where the castle comes in, is because inside the castle, you have the iron maker, you have the people that are growing the food, you have the people that are feeding the animals. Like there's a whole community working together here to support that castle system. It can't just be everybody does the same job, right? So
Yeah,
that was like a real aha moment in my life when I was like, and that this goes to a question that I was dying to ask you and forgot when we last interviewed or talked on the podcast, was about testing methodologies. Remember, I did call you after and I said, Andie, I have these different situations or scenarios. How should I go about testing? And the question was like, do I take, like in chemistry samples, we take tons of different samples and then we mix them all together homogeneously and then look at it so we get an overall view of that.
right.
But when you're in a microbial world, like I typically will look for above surface trends. Like, okay, there's a group of these types of plants over here that aren't over there, so I'm going to test both areas to see what the heck's going on.
Mm-hmm.
But then I got into that whole, like, should I take a core the actual plant, the rhizos sheath, for lack of better words. But in doing that, I could give myself a bad reading, or I could give myself a really good reading, depending on what pocket I hit. And that's when I just went, oh my God, this is way more.
What's the point?
Yeah, right. So
why bother? Yeah.
Yeah, that's when I called or texted you. And
Yeah.
I'm like, I don't know what to do.
Yeah, I mean, so my take on soil biology sampling is that of course it's like super like if you actually think about what's going on in the rhizosphere, it's very complex, and it would be it's proving to be impossible to really get a reading that could possibly account for all of that complexity, right? So what we can do is try to get a read on general markers of soil health, things that are associated with the processes that we're talking about today, like evidence of the players, the biological team that is necessary to be transforming particulate organic matter into mineral associated organic matter, and overall causing aggregation in the soil. So that's what I'm looking for on the microscope. Now that's coming from someone, again, that's like very focused on applied science. And if I was a researcher, this would be way more maddening. Like, you have to figure out how to sample, because it would be so dependent on the area of focus for the study of like, oh, am I going to like sample root hairs? Am I going to put aggregates under a microscope and do like light and dark field microscopy and not shake it, not break up the aggregates and look at it, which is what I do. We actually we're trying to break open the aggregates and put a sample under the microscope to try to see who is in there, where like if you're trying to find more in situ information and see how communities differ along a root sheath, you're going to go about it really differently, kind of in the way that you did, Leighton. And so that's why I'm excited about, Matt Powers recently came out with a new book called Regenerative Soil Microscopy, and he has a course to go with it. And he's showing people like us, who are really interested in this, all of the different ways you can use just a microscope to assess the different kinds of questions that you might have within a given context. So, as somebody who's really focused on mycorrhizae colonization is going to use the microscope differently than I am when I'm more focused on, are we seeing evidence of a healthy microbiome in general starting to form and cycle nutrients for you? And is it the kind of microbiome that is going to support the formation of soil structure and so on? And so, yeah, I shared with you what I do, Leighton, which is just take a representative sample according to the above ground conditions. So like, do not mix a sample from the field that's doing the worst with a sample from the field that's doing it the best and call that a representative sample. We need two representative samples to see if we can determine if there's differences, significant differences in the microbiome of those two different locations that are experiencing differences above ground.
I can't believe we're already an hour and a half into this. We're having it's just scratching the surface of this conversation. Yeah, interestingly enough, I've been working, obviously out here in California, playing with different recipes of compost that are coming in all as waste streams. So I'm trying to like upcycling these different materials and trying to figure out, how both to deal with the environment out here, which has been very difficult to say the least. I mean, the humidity is extremely low. So you're fighting the evaporation or transpiration of the compost moisture very quickly. And then you got UVs. And this is definitely outside the topic that I wanted to have, but I think it's an insight that might be beneficial for the community here. And that is, and again, I want you guys' theories on this, is that when you have a surface, a piece of organic matter that has gone hydrophobic, so it's shedding water, like you put water on it, it just runs right off of it. What happens when you have that condition in your soil? Like in Kyle and further east, you have this soil that's so friggin' dry that you pick it up and it just falls through your fingers. You probably have the same down there in Texas, right, Andie?
Mm-hmm. Yeah, for sure.
So you're applying microbes to that, and they're just like oxidizing. Like, and I have this experience. This is something that I've been working on for a few months now, and struggling with, because when I've taken compost that has gone somewhat dry, and I'm not talking like dust dry, but like definitely not like brownie moist cake type, and I've applied microbial mixes to it, and I lose the vast majority of my protozoa and nematodes. And I'm like, well, is it that the surface tension of a hydrophobic piece of organic matter is so strong that it literally sucks the water or cytoplasm out of these organisms? What do you think on that one?
I mean, in the case of hydrophobic conditions, there's just no way for the microbes to integrate into the rhizosphere where all their resources are that they need to survive. So I don't know that it's necessarily, furthermore, they're like kind of exposed to like UV exposure, wind, like other sources of erosion. So that's something to consider as well. But if you could, even if you have pretty harsh conditions, like summer applications when like UV is really high, you can still have success in biological applications. You just need to do it under the right conditions. So after a rain event, great time to get your biology out, right? And making sure that you do have plants in the ground, that's like all the more reason is to like, it's not just for that. Having plants in the ground is like a soil health principle for so many reasons. And one of them is that it's actually shading the ground and protecting it from the temperature and the UV. So like whatever biology you do get to the soil surface, even if it's not totally integrated, it kind of like buys the biology time if that little microclimate exists below like some type, even if it's a short little cover crop, you know? So that's really important. But then furthermore, that cover crop is providing the kind of exudates and things that a microbiome generally needs to get integrated into the rhizosphere. So yeah, that's my thoughts on like why it's also a chicken and egg thing. It's like you kind of need the biology there and the plants there in order to like, get the cycle going. So in some cases, this means that you need to be really strategic with irrigating. Like in some cases, you might have to have the infrastructure to irrigate to like get the system established, and then in theory it should be able to take care of itself, right? So taking advantage of like wet years when they're here and like, you know, making your expansion plans or whatever. Like you just really, again, harping on context here, but that is like so much of what I do is like thinking about all of the principles at play in nature and like how to leverage them to make sure that the way that we're participating is actually able to make a difference and move the needle, rather than us just being like looking at our calendar and being like, well, it's spring, it's time to apply a compost extract, and not really considering like the soil moisture conditions, the whether or not we have a leaf litter on the ground, like all of those different kinds of things we've been talking about.
I would love to like expound on this hydrophobic idea and like the acceptance of this, because I think that is something that people don't necessarily think about, like you said, Andie. But it also goes back to basic water chemistry. So when there is not enough water in a particle, I'm going to back up actually further. There's two things that a water molecule does. It adheres and it coheres. It adheres to other things. It coheres to itself. Okay. When there's not enough water to have free water in the soil, eventually when it gets dried down to a certain point, the adhesion, that magnetism that we've been talking about, molecular magnetism to the soil surface, the soil mineral surface, is so strong that no biological organism can actually pull it off. We call that the permanent wilting point when it applies to plants, right? The soil, the roots literally cannot suck the water off the soil surface. And the same thing happens to the biota. When it's too adhered to the soil particle because that magnetism is stronger than what the microbiota can generate, then it's not going anywhere. And the cohesion principle goes back to, that's personally my theory, Leighton, about what you were experiencing with the screening. Like it was forming that Rice Krispie thing. I think it got so low in water that the water molecules actually started causing things to ball up because of that cohesion to itself. But what you were saying, Andie, going back to like microbes literally not being able to process in those low water conditions, also ties back to what we were talking about earlier with this paper, this idea of microbial metabolic limitation. They literally say in the paper, Microbial metabolic limitation is when conditions still limit but do not entirely inhibit microbial activity. Thus, MML is controlled by the availability of energy, nutrients, and moisture to microbes. If there's not enough water, they can't process anything. They can't do anything because they can't get those nutrients. They can't get those resources that they need. But that hydrophobicity concept is really important. And I think you're doing such a good job explaining why that microclimate under a cover crop, under mulch, with the right irrigation scheme is so important to proper soil management.
In every way, it's kind of beginning to answer the questions that we've all had. Like, how do we regenerate these dirt? This hydrophobic sandstone clay with very little organic matter in it, and these are some of the starting answers. Yeah, each site is independent. Each environment's going to have different scheme of whether, you know, what best technique to use. Something that I'm going to try to do on this project next is to create one of those microclimates where I can actually grow a cover crop on the compost to support that or prevent that hydrophobic, you know, top 3-4 inches from happening, because it's real. I mean, and we get a nice breeze up there at Peach Hill, but that breeze is making it even worse because it's literally pulling moisture out of the compost and increasing the depth of that moon dust on top of So anyway, normally at this time I break and we take questions, and we've got 5 of them, and I'm sure we're not going to get through them, but I think the important thing is that you guys, we start talking about the next time that you come back, because we just scratched on this, and there's so much more that I'd love to chop up with you guys, because I think this was a really informative way to better understand compost extracts, applications, whether it's you want to use it as a solid or whether you want to liquefy it and make it a DOM. So again, definitely got to do this again, gang.
I agree. And we're only on page 16. I mean, like, you know, 66-page report. So we'll jump into the questions here right away. Do roots of common milkweed and similar root types help aerate the soil, or will these roots outcompete neighboring perennials? Are there other roles roots play in soil health?
Wow, that's a deep one. So typically milkweed is going to be grown in a riparian system, so a very moist soil. Interestingly enough, Phragmites are a really interesting plant. And I don't know if you knew this, you guys, but they grow in riparian systems right on the edge in the mud in a completely anaerobic soil. And the plant actually pumps oxygen down from inside of it into the rhizosphere to create enough oxygen that they can support biology that can degrade and pull nutrients out of that incredibly harsh environment. And I think milkweed is the same. But do either one of you guys want to expand on that?
I know milkweed, as riparian, but then there's also like native milkweeds here that are more like prairie plants. So I can't speak to that plant specifically, but the rest of the question, I don't know if you can show it again, Ken, but it was, you know, focusing on if it helps aerate soils, or will these roots outcompete neighboring perennials? I try not to think about, while I'm sure there is some level of competition for resources among like anything in nature, I try not to think that way first. I think about what are the conditions that are preferred by any type of plant, and what is it that I can do as a steward of that landscape to participate in the conditions I want to grow the plants that I want. So if you have a lot of milkweed growing and you're noticing that you would like to have more diversity or whatever, instead of thinking that this particular plant, and this happens with, you know, weeds, indicator plants of all different kinds, is they'll grow almost like a monoculture, it's not necessarily that they're out competing other plants, it's that the conditions are right for that plant to be growing and they are wrong for the plants that you want growing. So it's just a perspective shift to think about, how can I start improving the soil structure, for example, is usually what a lot of more perennial plants really want, is improved soil structure, rather than these compacted soils that require kind of a taproot to start generating that type of succession towards a more aggregated soil.
Yeah, and I would love to contribute. The question was kind of posed as an or, will it aerate the soil or will it outcompete? It's not really an or in that situation. I mean, all plant roots can really contribute to the aeration of the soil in that they create channels for air to move throughout the soil once those roots start to decompose. And all plant roots go through cycles of erosion and decomposition. So any roots in the soil is going to help bring oxygen into the soil environment. And then there was the final piece of that question, which is, do roots play other roles in soil health? And the answer is yes, like 1 billion. They support biology, they promote aeration, they promote soil structure development. Those are all, they actually promote moisture movement. There's evidence that they pull water up from deeper in the soil and drier environments, and then at night release it into the shallower elements of the soil. I'm blanking on the terminology for that right at this moment.
Like transpiration?
It's like a special thing to describe the water from the subsoil coming up and then being released to the surface soil. It's hydraulic something.
Yeah.
Anyway, I'm sure it'll come to me at 9:30 this night.
3 in the morning and wake you up.
Yeah, I'll be like, oh my God. No, but they do a ton of stuff, and that's why Andie's been hammering this point home this whole time. Grow plants on the soil. Keep it covered with plants. It's good. Certain plants are definitely better than others for the whole ecosystem, but grow plants.
But at the end of the day, the plants even the ones that we call weeds or indicator plants are just trying to rebuild the soil. Right. Yep. So let them grow, let them die, let them, leave the leaf litter, and let them come back and evolve. And eventually you will get something good. But we humans live on human time, not geological time, which is the problem. Really.
Weeds are medicinal plants for your soil, just like they're medicinal plants for us generally, like the milk thistle.
Mm-hmm.
So many.
So we'll go to the next one, perpetual. And how to make this DOM, liquefying it mechanically, is what we don't learn. Leighton's trade secret livelihood. Leighton, would you like to tackle that one, brother?
I use a washing machine. I'm not kidding. So I take a washing machine, tear it apart, make some adjustments. I add aeration sweeps down along the agitator, and that they go out into the vessel and sweep the sides. And because I'm pumping air down there, the air blows the material up to the top, and then it hits the agitation and goes back down. So I'm creating like a torus inside the washing machine while it's agitating. And you can do this with a 5-gallon bucket and a paint spinner on a cordless drill. It's a little bit more labor intensive, but anytime you can soft collide pieces of organic matter together, you're stripping off the humic and fulvic acid, you're releasing the spores of the fungi, you're releasing all the protozoa that were glued to that material, you're releasing everybody. So not only are you providing food, you're providing them with water, because this is a liquid suspension. You're generating some magnetism through the collision and friction that's happening when the materials are banging up against each other. So you're creating the perfect environment for a powerful compost extract that will adhere to the soil that you're putting it on. Again, in context, if that's a healthy soil that can allow it to penetrate, then yes, it works great. You squirt that stuff on like hydrophobic soil, like whether it's the dry version or the crusted version. Either way, you're not going to get a very good benefit from that.
Think Frenchy Cannoli, guys, and the system that he created, to form the vortex. So the soft collision, like Leighton was talking about, it's the same principle. It doesn't take a washing machine only. There's so many variety of ways that you can create the same system.
Ken, by the way, I gave Frenchie that idea.
I remember you talking about a conversation in the car for several hours that you guys were in. Yes.
Smoking one of his spliffs, which I never should have done.
Not while you were driving, no.
Anyway.
Andie, Maggie, do you have anything that you would like to add to that?
I just had a thought when you said soft colliding of molecules. Is that how you described that, Leighton?
So it's like if we were standing in a pool and I punched you under the water, you'd feel the impact, but it wouldn't hurt you. But if I punched you above the water, it would hurt, right? So it's using the methodology of like it's just brushing each other strong enough that there's a release, but it's not an impact that's going to damage.
Right. It made me think of, I was at a conference earlier this year, and there was a biodynamic workshop, and they had, just to get volunteers in on it, they prepped some of their biodynamic magic. I don't know, it's kind of like magician work, wizardry. But yeah, they put it into like 5-gallon buckets and then had volunteers come and use their arm, like stick your arm in the bucket and just move it clockwise and get like a torrent going. And it's like, it's very meditative. And then you go back the other direction. And that was like, it seemed the way that was presented was more of a ritual. But I think that sometimes those kinds of ritualistic things have like a scientific reasoning underlying them. And when you use that term, I was like, maybe that's why some of those biodynamics, those rituals are incorporated into the biodynamic preparations, is because you're generating a soft collision that is going to improve the impact of that amendment, essentially once you put it on the land.
Absolutely. And by stirring it, you're creating a vortex for the air to get down in there and create more biological or create less biological oxygen demand by increasing the dissolved oxygen in that liquid suspension. So it works for a couple different ways. But yeah, that was the cool part of biodynamics. Anyway, go ahead, Kev.
Don't forget the difference between the pumps you're using. An air pump with the piece that's moving back and forth, considering, the one that's slashing through the water, you're harming the biology instead of just making it flow.
So let me expand on that real quick. So you're talking about two different things. One is a pump for moving liquid. If you use a centrifugal pump, you're going to blow stuff up. And it's not because of the spin. It's actually because of the cavitation. The cavitation is what pulls them apart, makes them explode. Cavitation is like gravity. It's a very misunderstood phenomenon that occurs. And then you have pumps that move, air pumps that move air into the water column. And those you want to use, again, a lineal pump, not a regenerative pump. If you want to use a regen air pump, then what you have to do is you have to add a lot of hose to cool that stuff down, because those regen air blowers, they cook the friggin' air.
Cool.
Where what we call lineal air pump does not heat up anything. It just moves the oxygen. So just wanted to clarify that. I don't want people, misunderstanding and going awry.
Thank you for that clarification.
Yeah.
So are we ready for the next question? Maggie?
Oh, sorry. I just wanted to say about how do we make this DOM. The only point that I would have to add, is somebody who works a lot with like just soils that are like out there, and I garden a lot, like you don't have to make anything. It just happens. It's one of those things that it's in the root exudates, it's in the leaf litter. It's just that stuff that gets released that Leighton is like, manufacturing essentially by forcing that release of those molecules, by essentially making it so small that there's more surface area that these things get pulled apart. and those soft collisions, it does happen naturally. So like if you practice good soil stewardship and you in your garden apply mulch and compost and organic amendments and you do everything right, that dissolved organic matter is there no matter what.
Agreed, 100%, Maggie. And unfortunately, I'm called in on nightmare jobs where I have to resuscitate shit real quick. And that was
there's a context for everything. Oh yeah.
But I love the one straw revolution methodology. Less is more, right? Just do what you need to do, but let nature take its course.
Yep. So we'll go on to the next question from Case Gilmore, who's actually been on our podcast, guys. So you can go back and watch the interview Leighton had with Case. If the biology is diverse in the garden/ecosystem, will the introduction of a pest be enough to cause issues, or will the diversity ecosystem keep that introductory, I'm not sure what he's trying to say, pest in check?
The pest that was introduced.
Yes. Yeah.
So, Andie, why don't you talk a little bit on competitive exclusion?
Well, so my take on this is pathogens, pests, they're all around at all times. The possibility for them is always there, and you can consider that with through a lens of fear. Like, oh my gosh, they're always lurking. I will never feel safe from them. Or you can think of it through a lens of empowerment, which is, well, your best bet on having plants that are able to be resistant and resilient to a pest or disease introduction is to ensure that they have an abundance and diversity of microbial partners. So that's all we're trying to do all the time, is just improve the overall diversity of the beneficial microbiome so that you can outcompete or suppress and also promote plant health in such a way that pest and disease really can't take a hold and like tear through a crop like it would in a very common conventional system. And I used to work in controlled environment agriculture. So, vertical farms, indoor cannabis growing, greenhouses, and it was all chemistry based. And the intention was to always suppress biology. Like, you go in a bunny suit and you're, stepping in like antimicrobial stuff with your shoes and to not bring anything into the greenhouse. And they were terrified of an outbreak because it would destroy their crop like overnight in some cases. And that is really scary, but that's because they weren't leveraging the natural, the nature of how a healthy microbiome can really take care of all of that risk before you.
Mm-hmm.
Remember, there's no such thing as a pest. We invented that. Pests, they're there to recycle. They're there to take stuff out and down so that someone else doesn't consume it because it's not a healthy plant. And we are the ones that are causing unhealthy plants by using these synthetic forms of nitrogen, etc. Otherwise, if we were using the practices that our indigenous have been using for thousands, hundreds, maybe even millions of years, we wouldn't have any pests. We wouldn't have to kill a single thing. I'm sorry, I had to go there.
Yeah,
Look
totally.
at cancer. It's in every human body, but only an unhealthy body does it not fight the cancer off. It's the same with our plants.
Yep.
Yeah, exactly.
Maggie, you want to add anything?
Oh, no, I mean, Andie pretty much hit the nail on the head. A diverse biological suite that is appropriate for the context in which it is going to help be the armor against any major infestation of something that you don't want in that context. It's kind of the same idea. It's basically the biological idea behind integrated pest management, right? So when we talk about integrated pest management, we're talking about using multiple methods to prevent outbreaks of things that we don't necessarily want in our gardens and farms. So that may mean using diatomaceous earth and trap crops and mulching and watering the roots, not the leaves, like a bevy of things that we can do to keep things down. But on the biological side, it's the same idea. You want a robust community of microbes because somebody is going to eat that pesky fella, and you've got to have him there so that when the time comes, he can outcompete or eat or whatever that thing that you don't want in whatever context you've got him in.
Yeah.
Biodiversity.
One thing that I was thinking about recently is the fact that like a plant's defense is, because it can't move, like its main form of defending itself is going to be through like secondary and tertiary metabolites, right? And the only way they can generate those is through improved nutrition. And where does our improved nutrition come from? It's from a functional soil food web. So it all kind of goes back to how, you know, the plant is only able to do so much for itself based on its microbial partners it has access to. And there's even metabolites, like secondary metabolites, that a plant can generate to attract the predator of the particular pest that is harming them. It's incredible. I mean, nature has all the tools. It's just whether or not we're participating in facilitating everything that that plant could possibly need to be operating at that level of health.
Well, and the other thing I want to say too about nature does have all the tools. It does, but nature also endures a lot of death and destruction on a regular basis. So like an apple tree in nature is not going to produce a bounty of apples primed for human consumption. We have to modify that system somehow, be it via some control. But we can use the tools that nature has to make sure that the way that we do that is as least destructive or impactful as possible. Yeah. So, I mean, that's the problem that we're realizing with agriculture, is that we found ways to like make things perfect for the quantity of food that we need to produce using agriculture, but it's causing serious harm to the ecosystem around us. And that's the only thing that is supporting us on the whole, is the surrounding ecosystem. So we have to find ways to work with the tools that nature has to promote both ourselves and also the natural world.
Right. And anticipating that we're going to create disturbance, like we're going to disturb that plant microbe relationship just through harvesting, through, you know, through prepping fields in different ways. Even if you're doing it in as careful a way as possible, there's always going to be some source of ecological disturbance in agriculture. So I like to remind people that we're not trying to prevent disturbance at all. What we really want to be doing in agriculture is acknowledging that I am creating a disturbance. So I need to take the measures to respond to that disturbance. And that's where things like compost extracts come in. So like, if you know that you're going to be causing stress in the environment, like being in reciprocation, saying like, I know I did this to you, but here's an offering kind of
thing. If you're going to harvest from the system, you have to give back to it.
Yeah.
You know, there was a gentleman over in England that said you should only take 50% and leave the other 50% for the biota to take for themselves.
Wow,
and that's a beautiful thing, but humans are greedy. And you know, the one thing that really is important that we're not talking about is nutrition, human nutrition, right? You know, we grow these plants, you know, if we used biomimicry instead of just chemistry, we could begin to bring the nutrition back and allow the ecosystem to start to come back in to play and do its job. But that's why we're having these panels is to get the information out for people to better understand there are better ways than just chemistry, way better ways. And thanks for bringing up IPM, Maggie. That was great.
Yeah. So go to Case's other question. Any recommendations for corn borer in outdoor cannabis?
Check your biome, dude. You know, again, if you've got a super healthy plant, that corn borer is going to find something else. So, you know, there was a case where I worked with a cannabis grower up in Humboldt County a number of years ago, And they're like, oh, the deer always jump over our fence and they get in here and then they wreak havoc. And I'm like, well, why aren't you growing freaking cannabis around the outside of the fence? Give them something so they don't.
Yeah.
That crops.
Yeah, right. So grow some corn for that corn broiler, brother.
Yep.
Or sacrifice a few plants, one or the other.
Yeah, grow enough that you can lose some and not worry about it. So Case had one last question. It's the last question we've got. What do the ladies know of fulvic humic acid and their ability to help plants absorb nutrients?
Oh, damn.
Oh, that's a good
That's
one.
a long one.
I think I can do this. I'll give my 2 cents. I'll try to keep it brief, but because I wrote about this recently on like how humic acids work, and it's basically humic and fulvics are carbon based, and that's what makes them so useful, is because carbon is such a stable atom, and so when you have a molecule that's largely carbon based, it can, in the case of humic and fulvic acids, it can react to, it can basically bind nutrients to it, or toxins, actually. So that's why it's useful in situations where you're still using synthetics, you're still using pesticides and herbicides. Pairing a humic into your regime can be helpful to at least taking up the excess of toxins, or remediating a site where like you are no longer using that stuff, but it had been used in the past on that land. In terms of like nutrients, same concept. There's a nutrient that can bind to a humic acid or a fulvic acid, and then it's kind of loosely held. So it's a Goldilocks zone. It's like the attraction is strong enough to keep things from leaching, but it's light enough that a plant or through microbial activity could actually receive that nutrient. Excuse me, hold on.
I hate when that happens, Andy. Hang on. Yeah,
I got too excited. I got too excited, yeah. But in my understanding, as far as like when to use humic and fulvic acids, is fulvic is for foliar, mostly because it's a smaller molecule, so it can actually be absorbed through plant leaves, whereas like humics won't be so successfully taken up. And both of them are capable of, basically in fulvics, it's chelating the nutrient, which means it's binding a nutrient to it, and then it's small enough that a leaf can actually take it up, but it remains soluble, and that's important so that the leaf can like immediately use the nutrient that was bound to the fulvic acid. And so the same thing is kind of happening with humic acid, but just in the root zone. That's my understanding of humics and fulvics.
All right, one little added caveat. The atomic weight of a fulvic acid allows it to penetrate individual cells. So that fulvic can go into that cell and provide all kinds of enzymatic processes and folding proteins and giving that cell a more robust tool belt to do its interactions and reactions. So, but you're spot on about the rest. They chelate. Like whenever anybody calls me with a rescue, it's humic acid, TM7, so you're getting your trace minerals in case they're missing. Kelp meals, water soluble, something that's going to relax the plant, give it some hormones, and then biology. And generally speaking, I've never had anybody call back and say that didn't work. So the humic and the fulvic acids are a critical component to that rescue. All right, do we get through? Go ahead.
Sorry, I wanted to chime in on one point there. I'm not going to pretend like I am more well-read on Andie about that, because she literally just wrote about it. So like, whoa, yeah. She knows what she's talking about. But this idea of taking the nutrients and allowing the plant to access them later, if you want to read more about that, it would be considered nutrient buffering in like organic or potted soils, containerized soils, that sort of like manufactured media, and cation exchange capacity in our mineral soils. So just terminology to help people Google.
Yep.
Was that the last question, Ken? Or
that's it, guys. Leighton?
I was going to say you guys are rock stars. Thank you so much for coming on to this and having this conversation, because, again, this is like the most important part of this podcast, is giving people tools and better understandings on how to make smart choices in whatever conditions that they are or whatever they're dealing with. So can't thank you enough for giving us 2.5 minutes, 2 hours, 5 minutes of your time, of your valuable time, to helping the audience better understand some of these very complex processes. And Ken, as always, thank you, brother, for doing all the work behind the scenes and making this happen.
Not a problem. Andie, do you have anything to add? Are you going out and doing any talking events or anything like that people can check out?
I write regularly on Substack through Soil is Sexy is the name of my Substack. So just a playful part of the internet to talk about all of this fun stuff. And I have some presentations, but they're more local stuff. I do provide microscope assessments through my business Rhizosphere. So if you're interested in evaluating what you have going on in your soils, I'd be happy to take a look at that, or your compost as well, because that's an even better place to start, is checking out your amendments to make sure it's what you want to be applying.
Maggie, how about you, young lady? Were you doing any events?
Yeah, so I will be presenting with the company that I work for, Pit Moss, at Cultivate 24, which is in Columbus, Ohio. We will be giving a talk on determining the true cost of your substrates. So if you grow plants in containers, we sell, peat reduced and peat free media, but people aren't always sure of how to determine the full cost. So both to yourself and also to the world around you of your substrates. So that's what I'll be talking about. I'd love you to come say hi. I will be at Cultivate, just at our booth as well. Other than that, I don't think I have any other speaking engagements, and I recently got off most social media for my own sanity, if I'm being honest.
Totally.
But yeah.
And we're going to have both you ladies back on in the near future to continue this conversation.
Yeah, we have a group text going, so I'll ping them and let them figure out what's convenient for them, because I know you guys are both busy and it's summer and you should be enjoying your lives. Not on 2 hours of podcast with me.
I know, plus the hours of reading a 66-page paper.
Yeah, no kidding. What homework?
I have another one.
Oh, maybe it'll be another beach read.
No, that one I'll save for the winter. All right.
We have nothing better to do.
Yeah, exactly.
Guys, as for the channel, of course, we have Andie Lopez and myself on Wednesday, Gardens the Untold Story. We're going to be talking about fractals and the mathematical equation related to that, and how a lot of things work on that side. It's really it can be an interesting conversation. And then on Friday, I'm actually going to be interviewing Andie Lopez about his life and how he's come to be the invisible gardener. So, and next week we're still working on a guest for the show for Leighton. So stay tuned for that. But other than that, guys, peace out, everybody. And I'm going to end the broadcast.
Bye.